All right. So I guess I'll get started. My name's Matt Owers. I'm from Macquarie University in Sydney, Australia. So I'm coming to you some hours in the future compared to the majority of you, I guess. It's 10 p.m. at night here at the moment. So it's well and truly into the night time. But I'll be talking to you about something that I've been interested in for some time, the interaction between the ICM and galaxies in emerging clusters. And I just want to start by thanking the organisers for giving me the opportunity to talk to everyone about this topic, because I think it's kind of interesting as well. So I guess I'll start with a little bit of motivation as to why we might be interested in galaxy clusters. And this is viewed through the lens of my own interests. So people may have their own interests as to why they might want to study galaxy clusters, but my own interests lie in understanding why galaxies look the way they are and why things correlate with the environment. So we've known for a long time, actually, since the 1980s, that the morphology of a galaxy correlates quite strongly with an environment. And this is the well-known morphology density relation from Alan Dressler in 1980, which tells us that in the dense cores of rich clusters of galaxies, we're more likely to find S0 and elliptical type galaxies that are devoid of star formation when compared with the lower density field environments where we see a larger fraction of spiral galaxies rich with star formation. So more recently, surveys like the 2DF GRS, which was conducted here in Australia, the Sloan Digital Sky Survey in America, and the Galaxy and Mass Assembly Survey, also conducted here in Australia, have really nailed down some of these correlations with the environment. In particular, have focused as well on what the star-forming properties of galaxies look like as a function of environment. We see fewer star-forming galaxies in the rich cores of clusters. And we also see that the star formation rate of star-forming galaxies decreases as you head towards the centers of groups and clusters of galaxies, all of which indicate that the environment is an important in shaping the properties of galaxies in terms of their morphology and their star formation. And I guess now the big question is trying to understand what drives these correlations. And here again, I think clusters are really important. They're the densest regions that we see in the universe. They host a plethora of different environmental processes that we can investigate within these regions. And this is, I think, shown quite nicely here in this slide that I stole from R.E. Chung, who basically has given a schematic showing what a galaxy goes through in its everyday life as it resides in a galaxy cluster. And this is sort of broken into interactions, gravitational interactions, for example, tidal and compression and truncation interactions with the gravitational potential well of the cluster as a whole that can drive star formation in these galaxies. Harassment, which can also drive star formation, but also pulls gas and stars away from the outer parts of galaxies, changing their morphologies and potentially stopping their star formation. Mergers, probably not so important in the cores of clusters where the velocities are probably too high for things to stick together, but may be important in pre-processing as groups fall into clusters. Some of the things that I've been more interested in and I'll be talking about a bit later on are the interactions with the ICM and galaxies. So one of the more well-known interactions is that of rare pressure stripping, where the wind felt by a galaxy as it rushes through the intracluster medium strips off gas and stops star formation in the galaxy without significantly altering the morphology of the stars and the distribution of stars. And you can see some spectacular trails of gas and star formation that we'll look at a little bit later on in these rare pressure stripping events. There's also other aspects like starvation, which is probably important on long time scales and may well be important in groups and also in the outskirts of clusters in terms of reducing the star formation of galaxies in clusters. So that's basically, some of the processes that a galaxy feels in just a normal, relaxed, everyday sort of cluster. But what about cluster mergers? So why are they important? Well, cluster mergers, the major merger of two clusters is the pinnacle of hierarchical structure formation. So it's one of the most it is actually the most energetic event in the universe after the Big Bang. So if you've ever read a paper describing the major merger between two clusters, you will have come across the line that, you know, they release 10 to 64 ergs of energy, and most of that goes into driving shocks and compression of the intracluster medium, as well as speeding up the galaxies as they collide. So these clusters collide at somewhere of the order of 3,000 to 4,000 kilometers a second. So there's a lot of interesting stuff that can be learned from these clusters in terms of intracluster medium physics that we can learn from shocks and cold fronts. We can learn a lot about the ICM. We can learn a lot about particle acceleration by observing radio halos and relics that we see in these clusters, cluster mergers. We can also learn a lot about dark matter physics, and everyone, I guess, will be familiar with the bullet cluster and the impact that it's had on understanding dark matter in our universe. You'll also know from Gabriel Pratt's talk yesterday that we need to understand cluster mergers if we want to use clusters as cosmological probes for scaling relations and all that sort of thing. They can really muck up the scaling relations for mass measurements of clusters. So the other thing that's really interesting is that these violent environments probably drive enhanced or accelerated galaxy evolution. And it's been an open question for some time as to exactly what happens in these cluster mergers to galaxies. So the high speed mergers, as I said, drive shocks, compression of the intracluster medium, whether this strips galaxies of gas and leads to quenching of star formation, or whether the enhanced pressure leads to triggering of star formation, is sort of an open question that we've been trying to address for, I guess, over 20 years now. And I think the punchline of this talk will be that we aren't quite there yet, but you know, if someone's willing to do the work, we probably can get there in the next 5 or 10 years, I hope. I'm probably not going to do that work though, so maybe one of the younger PhD students might want to address that. So I guess for the rest of the talk, I'm going to go over a few different ways that cluster mergers can impact the unfortunate galaxies that are involved in these cluster mergers. So I'll start with just a few simulation results, so idealized simulations that have been used to try and understand the impact of cluster mergers on the resident galaxies. And then I'll go on to talk about what's been done observationally to try and look at whether these cluster mergers in fact enhance star formation or whether they preferentially quench star formation during the merger process. So the first port of call here is to try and understand or to look at simulations that show how the high-speed merger process can strip potentially star-forming gas from these galaxies. And I think this has been looked at over 20 years ago now by Fujita and other people. But I think that this paper by Domenko, whose main aim actually was to look at the enrichment of the intracluster medium due to ram pressure stripping of satellite galaxies, is probably one of the better showcases of how mergers impact galaxies because of their increased ram pressure. So they looked at three idealized simulations of three clusters, two of which had pretty benign merger histories. They underwent some minor mergers, so mass ratios of less than 1 to 4 or so throughout the course of their history. And they also looked at one cluster that underwent a major merger of around about a 1 to 3 mass ratio at around about a time of 4 billion years. And so what they looked at was the mass loss rate as a function of time. That's what's plotted down here. And you can see that at 4 billion years timescale, the mass loss rate from ram pressure stripping in the merging cluster, which is shown by the solid line here, increases by an order of magnitude. And again here at around about 7 billion years, when the subcluster turns around and comes back for its second pericenter. So I should say this coincides with the first pericenter passage of the cluster merger. So you can see that there's a strong enhancement of the ram pressure due to this high speed, several thousand kilometer a second cluster merger that's going on in this cluster number 2 in their simulations. And they didn't talk about quenching of star formation in this paper, but it's not too much of a stretch to imagine that this enhanced ram pressure stripping that's felt during this cluster merger undoubtedly leads to a more significant and a more accelerated quenching of star formation, just because there's just no gas left in these galaxies in order to form stars anymore. So we might expect that major mergers, given this simulation, drive quenching of star formation rather than triggering of star formation. So another idealized simulation was done by Kenji Becky, and the idea here was to try and understand thanks, I've got that 10 minutes to go, the impact of mergers on triggering star formation. And again, this is a very idealized simulation, a 1:4 mass ratio merger of a 10 to the 14 solar mass cluster. And what he wanted to do was just to investigate how the surrounding pressure of the intracluster medium that was felt by a galaxy in this merger process changed. And you can see as for a single test particle as a function of time, you end up with these very strong peaks in the pressure felt by a galaxy during this core passage phase of a major merger. Looking at the ensemble of the test particles in this idealized simulation, you can see that the maximum pressure felt peaks at around about 3 to 4 billion years at the time of this core passage phase. And it's around about 10 to the 6 in these units, kelvins per centimeter cubed, times by the Stefan-Boltzmann constant. And that is over an order of magnitude higher than the required pressure to collapse giant molecular clouds to form star formation. And this happens to a large fraction of the galaxies involved in this idealized simulation of a cluster merger. So that tells us that this idealized simulation shows it is possible to simultaneously trigger star formation in a large fraction of galaxies if they have gas during a cluster merger. So Elke Rodiger looked at this in a little bit more detail. She, again, using idealized simulations, tried to understand the impact of a merger shock on a disk galaxy that's currently forming stars, gas-rich galaxy undergoing star formation. So what happens if if this is overrun by a shock that's traveling at around about 2,000 kilometers a second? So what she found was that the pressure felt as the shock overran the galaxy, only for around about 20 million years or so, was able to trigger star formation in the outskirts of the galaxy. So in regions outside of the sort of central 5 kiloparsec regions of this galaxy, star formation was triggered by that shock passage, and the prevailing wind that followed was able to strip this compressed gas away from the outer parts of the disk, where it was able to form stars at a later stage, and ended up with this sort of jellyfish-like morphology, which we'll talk a little bit about later on. So this morphology can persist for somewhere around 10 to 100 million years after the passage of the shock front over this galaxy. So these simulations, idealized as they may be, indicate that this violent environment, so the core passage phase where there's shocks and all that sort of thing, high-speed shocks driven into the intracluster medium, are capable of affecting the star formation of the resident galaxies. So, it's possible that you can have enhanced quenching, or you can also have this triggering of star formation, although it's only at sort of a factor of 2 to 3 over and above what the star formation is in the galaxy before it was overrun by the shock. It is possible to impact the star forming properties of galaxies during a cluster merger. So what do we see in the observations? So the first set of observations that I'm going to talk about come from clusters observed with the Sloan Digital Sky Survey, and it's from a couple of papers written in 2014 and 15 by Cohen et al. There's also a follow-up paper by Yoon that found similar results that I won't be showing any plots from. So basically what Cohen did in 2014 was they went and got 100 clusters from the Sloan Digital Sky Survey, and they used the INASTO catalogue where they had basically used a clustering algorithm to fit normal Gaussian mixture models to each of those 100 clusters and determine how many subclusters were required with that clustering model. So what Cohen did was then use the H-alpha from the spectroscopy from the Sloan Digital Sky Survey to measure the fraction of star-forming galaxies in clusters as a function of the number of components required with this clustering algorithm. So this number of components is a proxy for the merger or the relaxation or the dynamic of the clusters. So clusters that have more components presumably are undergoing more rigorous merger activity. Similarly, over here in 2015, they used a slightly different way of defining dynamical activity, and that is the symmetry of the R-band light distribution in clusters. And they looked at the star forming fraction here. Overall, they find the fraction of star forming galaxies increases with the mergers, but it's a kind of small result there, and there's a lot of scatter in this diagram. And so you can imagine that perhaps a more stringent identification of mergers might give better results. And this is where Andrea Astro's work comes in. She looked at 19 clusters in 2017, 8 of which were relaxed, 11 of which showed evidence for merger activity based on the existence of radio halos or radio relics, which really indicate that there's been a post-core passage major merger happening in these things. She collected H-alpha observations for around about 3,000 confirmed cluster members in these clusters, and compared the luminosity functions, the H-alpha luminosity functions of relaxed and merging clusters, finding quite clearly that there is an offset in merging clusters in the sense that the luminosity function shows a larger number of H-alpha or star-forming galaxies in these merging clusters. The interpretation there was 2 interpretations. The favoured one was that these mergers are probably triggering star formation, which is increasing the fraction of star-forming galaxies in these clusters. She also compared the merging clusters, those with relics, so those that show evidence of shock fronts, with those with halos, radio halos, finding a slight difference between the two. And putting that down to the fact that potentially those with relics are younger mergers compared with those with halos. So there have been a number of investigations on single or a couple of clusters in the literature investigating the impact of cluster mergers on star formation. And as you can see, I've kind of listed these here, those that show enhanced star formation, those that show both enhanced and star formation and enhanced quenching, and those that show no enhanced star formation or quenching. And so essentially we're 50-50 split as to whether there's enhanced star formation in cluster mergers or whether there's enhanced quenching. And I think that it really comes down to understanding the merger phase of the clusters. And that was shown here in these 2 clusters here by Huang and Li. So 168 is a post-core passage major merger. You see in between the clusters evidence for star formation. Abel 1750 is pre-core passage. You don't see any evidence for star formation. And so I think that it probably makes sense that understanding the merger history of these cluster mergers is imperative in trying to understand how these impact star formation. And we probably need to investigate a large sample of clusters with different merger stages to understand this. So in the last minute or so, I just want to talk about jellyfish galaxies. So these are galaxies that show are evidence for quite strong ram pressure stripping. So they were first found in 2006 by Owen et al. In the Abel 21-25 cluster merger. They show they're a little bit different from previous known examples of ram pressure stripping in that they show star formation in the contrails of ram pressure stripped gas. And so they're probably more extreme examples of ram pressure stripping. So Owen et al. Found these in Abel 21-25, which is a known high-speed line of sight merger. And they attributed this extreme state to potentially due to the merger, which is driving this extreme ram pressure stripping in this galaxy. So there was a few more examples of these extreme jellyfish galaxies found in more relaxed clusters. So Cortese found these in Abel 2667 and Abel 1689. But then we looked at these in Abel 2744 and found 4 such examples of these extreme ram pressure stripped galaxies. And we found that they were relatively close to shock-like features in this really high velocity merger. So this 2744 is merging at around about 4,500 kilometers a second, driving a strong shock into the intracluster medium. And we found that these jellyfish galaxies were coincident with shock-like features in the intracluster medium, which led us to speculate that potentially it was the merger, the high-speed merger and the shock front that was driving these features. But it was only one cluster of galaxies that exhibited this, and it needed follow-up of a larger sample. So McPartland looked at this with the max larger sample of clusters, the max cluster sample. And what they did was to, I'll go through this very quickly because I see some explosions going on in the background of multiple explosions. So what they found was that the jellyfish galaxies do appear to be found more preferentially in merging clusters, but there's some conjecture in this area now as well. And I believe that Darit will talk about her jellyfish galaxies later on, and also Anna Carolina Lorenko will talk about jellyfish galaxies later on, and whether cluster mergers drive this extreme ram pressure stripping seen in these jellyfish galaxies. I did have this one last slide on Andros' work, which uses IFU observations to investigate the distribution of H alpha flux in galaxies in the sausage cluster and their interaction with the merger and the shock fronts there, which seems to indicate that star formation may be driven by the shock fronts in this cluster. So that's kind of, Andrea might talk about this in her talk later on. So I'll just leave that there. So the summary, I guess the question of whether interaction between galaxies in the ICM during cluster mergers triggers or truncates or both star formation in clusters remains unanswered or equivocal as to both the different scenarios. And I think the likely answer requires quite a large sample of clusters to be investigated in different phases of their dynamical evolution. So relaxed, pre-merger, core passage, and post-core passage, or with different mass ratios and masses of the clusters, in order to have a sort of large-scale investigation of the star formation in these environments. And I think that future large-scale multi-object survey, spectroscopic surveys, such as Foremost, Weave, and DESI, combined with all-sky X-ray observations from eROSITA and deep radio observations will help in this regard. And also IFU observations look very promising. And I'll just point out that we're just about to start a new IFU survey, the Hector Galaxy Survey, which will investigate 11 massive clusters of galaxies, several of which are interesting in that they are undergoing major mergers currently. And I'll leave it